Students, this is physics chapter number 6, heat transfer, and this is note number 2. All right, this is the second note. We have been learning about boiling, evaporation, and today we'll be learning about thermal expansion, okay, and different types of thermal expansion. So first you need to understand what is thermal expansion. Thermal expansion is the tendency of matter to change its shape, area, volume, and density in response to a change in temperature. That means when a body's temperature changes, its shape, or when we change the temperature, either we increase or decrease, what happens to the shape of the body? That also changes, right? So that is what thermal expansion is. So thermal expansion is the tendency of matter to change its shape, area, volume, and density in response to a change in temperature. The next point I want you to understand is contraction effects. A contraction effect also is known as negative thermal expansion. Like a number of materials, they contract on heating within certain temperature ranges. This is usually called negative thermal expansion rather than thermal contraction. Like, for example, the coefficient of thermal expansion of water, it drops to zero as it is cooled to 3.983 degrees Celsius and then becomes negative below this temperature. Now this means that water has a maximum density at this temperature. Okay, this is almost like 4 degrees Celsius, right? 3.983 degrees Celsius. This is almost like 4 degrees Celsius. So at this means that water has a maximum density at this temperature, and this leads to bodies of water maintaining this temperature at their lower depths during extended periods of sub-zero weather. Now let's see factors affecting thermal expansion. Thermal expansion generally decreases with increasing bond energy. In chemistry, you must have learned about chemical bonding, right? So thermal expansion generally decreases with increase in bond energy or increasing bond energy, which also has an effect on the melting point of solids. So high melting point materials are more likely to have lower thermal expansion. Remember this, that high melting point materials are more likely to have lower thermal expansion. And in general, liquids expand slightly more than solids. Okay, we know that the intermolecular space, the intermolecular particles between in liquid is little far away from solids. So in general, liquids expand slightly more than solids. Now the next point I want you to also understand is that the thermal expansion of glasses is slightly higher compared to that of crystals. Alright, so the thermal expansion of glass is slightly more than the thermal expansion of crystals. And thermal expansion changes the space between particles of a substance. It all affects the intermolecular space of the particles present or that forms three different types of matter: solid, liquid, and gas. You already have studied about that the intermolecular particles in solid is much closer than in liquids. It's a little bit far away, and the further more than each other is in the gases. So thermal expansion changes the space between particles of a substance, which changes the volume of the substance while negligibly changing its mass. Okay, so it changes its density. The density also changes, which has an effect on any buoyant forces acting on it. I think you also have learned about buoyant force, the upward force that is in liquids. All right, so let us understand coefficient of thermal expansion All right, what do we mean by the coefficient of thermal expansion? Now, when we talk about coefficient of thermal expansion, the coefficient of this thermal expansion, it describes how the size of an object changes with a change in temperature. Okay, how the size of an object changes when there is change in temperature. Okay, so expansion in solids. When calculating thermal expansion, it is necessary, we know what is thermal expansion, right? When there is change in temperature, the shape of the body changes in area, volume, and length. So when calculating thermal expansion, it is necessary to consider whether the body is free to expand or is constrained. Constrained means forced. Alright, now if the body is free to expand, the expansion or strain resulting from an increase in temperature can be simply calculated by using the applicable coefficient of thermal expansion. In future, you will be learning more about coefficient of thermal expansion. Alright, so if the body is constrained so that it cannot expand, okay, free to expand, or it is forced not to expand, actually constrained. So if the body is free to expand, the expansion or strain resulting from an increase in temperature can be simply calculated, like I said, by applying coefficient of thermal expansion. And if the body is constrained so that it cannot expand, then internal stress, there is stress within the body. So the internal stress will be caused by a change in temperature. Okay, now let us see different types of thermal expansion. Alright, basically there are three different types of thermal expansion. The first one we'll be understanding is about linear expansion, that is known as linear expansion. Now, what is linear expansion? Linear expansion means change in one dimension, that means length. Okay, linear expansion refers to change in length as opposed to change in volume. Change in volume is also termed as volumetric expansion. So when an object is heated, if there is change in the length of an object, then that is known as linear expansion. Alright, now the second type of thermal expansion is area expansion, which is also termed as superficial expansion. Alright, now this area thermal expansion coefficient relates to the change in material's area dimension when there is change in temperature. So when there is change in temperature, if the area of the body changes, then that is termed as superficial expansion or area expansion. And the third type of thermal expansion is known as volume expansion, which is also known as cubical expansion. Okay, volume or cubical expansion. Now this means that when a solid metal block is heated, its volume increases. Right, it's quite simple, right? So these are three different types of thermal expansion: linear expansion, area or superficial expansion, and volume expansion or cubical expansion, which is the third type of thermal expansion. Now when we're talking about cubical expansion, like for example, a steel block, a steel metal with a volume of 1 cubic meter, it might expand to about 1.002 cubic meter when the temperature is raised by about 50 Kelvin. Okay, 50 K. So you notice here that you understand here that from 1 cubic meter, the volume of the steel block has increased to 1.002 cubic meter when the temperature is raised by 50 Kelvin. This means that the expansion is about 0.2%. Alright, so this was an example of cubic expansion. Now let us understand expansion in solids. We'll be understanding about expansion in solids, expansion in liquids, expansion in gases. So first let us see expansion in liquids. Okay, the thermal expansion of liquids is usually higher than in solids. Why? Because the intermolecular forces present in liquids are relatively weak and its constituent molecules are more mobile. That means mobile refers to movable, moving from one place to another. So the thermal expansion of liquid is usually higher than compared to solids because the intermolecular force present in liquid is little less because their molecules are a little bit away from each other as compared in solids. Now liquids, unlike solids, they have no definite shape and they take the shape of the container. We know this, right? Now liquids do not have a definite shape. They take the shape of the container. And consequently, liquids have no definite length and area. So linear and areal expansion of liquids have no significance. The other point I want you to understand about expansion in liquids is that liquids in general expand on heating. However, water is an exceptional case. Okay, water is an exception to this general behavior. We have already talked about this. Below 4.4 degrees Celsius, right? It contracts on heating, leading to a negative thermal expansion coefficient. And at higher temperatures, water shows more typical behavior with a positive thermal expansion coefficient. So here what I want you to understand is that water is an exception to this general behavior because below 4 degrees Celsius it contracts. Okay, so below 4 degrees Celsius it contracts on heating. So this was some points about expansion in liquids. Now let us see few points on the expansion in solids. Thermal expansion is very evident in solids as atoms are very close to each other, right? So thermal expansion is very evident. We can clearly see thermal expansion in solids. It is well known phenomenon now that substances expand on heating and contract on cooling. We all know this, right? Any substances expand on heating and contract on cooling. Now if you heat a body, its dimensions changes, right? It alters its dimensions depending on the shape of the body. Now the expansion can occur in length, in which case it is known as linear expansion, like we have already talked about this. If the expansion occurs in length, then that is known as linear expansion. If we take a square tile and heat it, the expansion will be in two fronts, that is length and breadth. Here the expansion is taking place in area, which will be known as area expansion. And if we take a cube and heat it, all its sides expand, and now the body experiences an increase in the overall volume due to this, and it is called volume expansion. Okay, right? Or it is also termed as cubical expansion. So these were a few points about expansion in solids. Now let us see a few points about expansion in gases. Thermal expansion or contraction occurs in a gas similar to that in a liquid. As in the case of a liquid, the expansion of volume is only important because gas do not have a definite shape, right? And the amount of volume expansion in a gas is much larger if we compare it to that in a solid or a liquid. That means a volume expansion is more in gas compared to solid or a liquid. And experiments show that all gases at very low densities, they exhibit the same expansion behavior. Okay, I'll repeat this once again. All gases at very low densities exhibit the same expansion behavior. And the change in volume of a gas also occurs due to pressure applied on it. temperature and pressure plays a very important role. The role of pressure on the volume of liquid or solid is not important in general. The volume of a gas increases, okay, when the pressure over it is decreased. That means they are inversely proportional. If one increases, the other decreases. That is what is referred to inversely proportional. The volume of a gas increases when the pressure over it is decreased, and it decreases when the pressure is increased. So these were some of the points for expansion of gases. So till now we have learned about thermal expansion. We have learned some factors that affects thermal expansion. We also learned expansion of liquids, expansion of solids, and expansion of gases. Okay, now the last point that we'll be learning in this note, and we'll obviously be finishing this lesson. The last point that we'll be seeing is some everyday effects of thermal expansion, okay, that we see in our lives. Some of the examples of thermal expansion. The first example is, if you have ever tried to unscrew a stuck lid of a glass jar, the cap of the glass jar, if you're not able to open it, you will very much appreciate this expansion effect. What you need to do is simply run some hot water over the metal lid. Just on top of this cap of the jar or the lid of the jar, pour some hot water just for a few seconds to heat the lid. Now what happens then? This will make the lid to expand slightly, and it should then be easier to unscrew it. So if you are not able to unscrew any bottle cap or lid, what you just do is you pour some warm water or hot water for a few seconds on the lid. Then what happens? The lid will expand slightly and it will be easy for you to unscrew the lid. The second application, or the second example that we can understand about thermal expansion, is regarding bridges. Bridges have a long span, and in hot weather the materials that the bridge is made up of will expand. Right? Bridges has to last for a long time, and the metals that are used to make bridge will expand during hot weather. So this could cause the bridge span sections to buckle. To avoid this, now what does this mean? That this might cause bending of the bridge, right, during the summer season or during the hot weather. So to avoid this, there are expansion joints. Okay, expansion joints are designed into the bridge so that the bridge sections can expand freely without buckling, all right, without bending. So this is another application, or this is another example of thermal expansion. Like in the bridges, you might have seen that there are joints. They are not completely fixed, right? There are joints. Now during summer season, this point at the joints, it expands, right, which keeps the bridge straight without bending. Now let's see the third example. A liquid, when heated, will expand and can be made to rise up a tube, right? A liquid, when heated, will expand and can be made to rise up a tube, like in thermometers. Thermometers use the expansion of a liquid, such as mercury or alcohol, to measure the temperature using calibrated scale. Alright, let's see another example. The cables, right? The cables that hang between electricity poles, right? I think all of us have seen that. The cables that hang between electricity pylons or electricity poles must have some slack on them. Okay, it should be a little loose to avoid the cables becoming too tight and breaking in cold weather. when the cable material contracts. We know that in high temperature the substances will expand, and in low temperature it contracts. So you might have seen that some of the electrical wires, they hang a lot during summer, right? They are not fixed very tight. Why? The reason is because during winter season it will contract, and when it contracts it might pull the pole also, right? So that is the reason why when they fix these electrical wires between the poles, they must have some slack, or they must be loosened and fixed. Okay, now the next example, we'll see just one or two more examples, and you can also see in your book some examples. Okay, the air in a car tire or a bike tire, all right, gets warm after a long journey, and this increases its pressure. The pressure in the tire increases in a long journey. Why it increases? Because the tire gets hot. So this is also because of thermal expansion. The other and the last example that we'll be seeing is about railway lines. I think you have seen that the railway lines, they have expansion gaps, just like bridges. Okay, so railway lines also require expansion gaps similar to bridges. Why? To avoid buckling in hot weather. We know that during hot weather, the metals will expand. So if there are no expansion gaps, the railway lines will bend and will cause many accidents. Alright, so these were some of the examples, and by this we have finished chapter number 6, heat transfer. I want you to go through the first audio note that I had sent you, and I want you to go through this note also. Okay, keep learning and keep learning well. You have to revise what you learn, what we learn here, what notes I send you and the other teachers send you. So you have to keep learning, keep reading your book. Okay, and after a few days, after maybe next week, I will send you the homework for the objective and then subjective questions, and I want you to submit your homeworks, okay, when I send you next week. So I hope you have understood what we have learned in this note. All right, so keep learning and keep studying well.